Welcome class, myself Professor D.S. Rai, Professor Department of Civil Engineering, BBD, ITM Lucknow. Today, the course that I am going to discuss KCE 064 Foundation Engineering. Today, I will take up lecture 34, Reinforced Earth. References that I have taken: Dr. B. C. Punamiya, Soil Mechanics and Foundation, V.N.S. Murthy, Soil Mechanics and Foundation Engineering, Alam Singh, Soil Mechanics and Foundation Engineering, and some material have been taken from internet. The contents: today I will take up foundation, bearing capacity of shallow foundation, shear failure, U by B more than 2 by third, shear above reinforcement, U by B less than 2 by 3 and N less than 2 or 3 are short tied, tie pulled out and N more than 4 upper tie break. VCR value in mode 1 failure for with a different soil, bearing capacity ratio, stress distribution below strip footing, assumed failure mechanism, bearing capacity ratio, typical geosynthetic SRF, geosynthetic reinforced soil foundation. First of all, we will take up foundation. Foundation is a part of a structure that transmits the weight of a structure and load to the ground. This is the foundation which distributing the load in a larger area, so that the stresses developed is lower. The soil does not fail in shear and settlement is within safe limit. Broadly classified, they are in two categories. First is a shallow foundation and second is a deep foundation. A foundation is shallow if its depth is equal to or less than its width. So, we will see here in this figure, this is a wall under which there is a strip footing, there is a strap footing like this way, it is quite clear. This is a spread footing like this way. This is combined footing, combination of all these, and this is a mat foundation which is provided where the bearing capacity of soil is very less. Now, come to the bearing capacity of shallow foundation. We will discuss Terzaghi equation for calculating bearing capacity. Here we can see this is the walls, this is the width of the footing, and here is a loading QU, uniformly loads are coming on the soil. There are 5 zones, and the first zone is a waste type which is directly underneath of the footing. So, this is the wedge and there is no deformation going outside from the edge. Second is zone of a radial shear zone, in which the radial type of shearing action goes on. The third is a passive zone in which this is a work like a linear shear zone. So, this is a brief of the bearing capacity of silo foundation, because whatever we will discuss that will based on this concept. Now, come to the shear failure. The bearing capacity failure is categorized in 3 types. The first is called general shear failure. We can see here in this diagram, this is the settlement and this is the stresses ultimate capacity. The second is a local shear failure. Again here is a QU. The third is a punching shear failure, in which the load is coming directly underneath of the footings and deformation or settlement occurs underneath. So, we will discuss one by one. That first is general shear failure. So, we can see here a strip footing is, this is assumption, a strip footing is rested on the surface of dense sand or a stiff clay. This is the assumption. Q is the load per unit area and S is the settlement. At a certain load intensity equal to QU, the settlement increases suddenly. Shear failure occurs in the soil at that load and failure surface extended to the ground surface. So, we can see here this is the general shear failure, in which the failures comes at the surface, and here is the abrupt change in the graph when load is coming QU on the footing. The type of failure is known as general shear failure. A heave on sides is always observed in general shear failure. So, this is about the shear failure. The basic assumption is the footing is rested on the surface of dense sand or a stiff clay. So, this is the basic assumption. Now, come to the shear failure, local shear failure. The strip is rested on the surface of medium sand or clay on medium consistency. When the load is equal to a certain value of QU1, we can see here this is the QU1. Okay. So, this is the QU1. The foundation moment is accompanied by a sudden jerk. The failure surface gradually extended outward from the foundation. We can see here again this is extended outside. In the local shear failure, the failure surface gradually extended outward from the foundation. The load is equal to QU. So, now come to the punching failure. A strip footing is rested on the surface of loose sand or a soft clay. The failure surface does not extend up to the ground surface. there are jerks in the foundation at a load of QU1. Again you can see here this is our the punching failure. So, this is the QU1 and here the failure surface does not extend up to the ground surface. There are jerks in the foundation at a load of QU1. The footing fails at a load of QU, at which stage the load settlement curve become steep and partially linear. There is only vertical moment of the footing, there is no horizontal moment of the footing. Now, come to the different modes of failures. We can see here is the U by V more than 2/3 means 0.67 shear above reinforcement. We can see here these are the reinforcement provided here below the our pressure bulb we can say, and the depth of this first reinforcement layer is a U and this is the width of the foundation. So, U by V should be more than 2/3 or you can say 0.67. So, we can see the shallow foundation on thin layer of soil with a dense reinforcement resting on a rigid boundary. Bearing capacity failure of soil above the uppermost reinforced layer. This kind of failure reinforcement is not effective, like to occur if the depth U is greater than about of the width means U by B is greater than 2/3. If the reinforcement concentration in this layer is sufficiently large to form an effective lower boundary in which the shear zone will not penetrate. Sorry. This class of bearing capacity problem corresponds to the bearing capacity of a footing on the shallow soil bed overlaying a strong rigid boundary. Now, again U by V less than 2/3 and N is less than 2 or 3. Here N is the number of bars provided or strip provided. So, here the condition again B is the width and this is the depth of first reinforcement from the bottom of the foundation. So, this is the U. So, U by B should be less than 2/3 means 0.67. So, shallow and a light reinforcement with short tie, this type of failure is likely to occur for the shallow and light reinforcement U by B less than 0.67 and no of number of reinforcement layer N should be less than 3. The length of reinforcement up to the shear zone is not effective for improvement of soil and the for supporting a silo foundation. This length of reinforcement beyond the shear zone is known as anchor, and the length of reinforcement. Again, the same condition, u by b less than 2 by 3 means 0.67, and here n number of bars provided is less than 2 or 3 are short tied, tie pulled out, and in this condition n is greater than 4, the upper ties break. So, here we will discuss u by b less than 2 by 3 and n is greater than 4. The shallow, long and heavily reinforced foundation with the applied load, the footing and the soil beneath the footing move downward, causing reinforcement to be deformed and tensioned. Due to its stiffness, reinforcement develops an upward force to support the applied load. A certain amount of settlement is needed to mobilize tension. We can see here, this is the condition, this is the u means depth of first reinforcement from the bottom of the footings. This is the bottom of the footing, this is the B. Now, the BCR value in mode 1 failure for with a different soil. So, BCR bearing capacity ratio will be equal to Q by Q0. Here in the diagram or a graph we can see this is the width of the footing and this is the U means the depth of first reinforcement from the bottom of the footing. So, we can see here the bearing capacity ratio Q by Q is going very sharply up like this way up to 0.5. Here depth ratio U by B is 0.5, means B is double or 2 times of the depth of the first bar from the bottom of the footing. Here U by B is equal to 1. So, here we can see the bearing capacity ratio Q by Q is very sharply decreased, and at U by V is 2, here the bearing capacity ratio Q by Q is almost as 0. So, now bearing capacity ratio. Bearing capacity improvement is expressed in term of BCR, means bearing capacity ratio that is Q by Q0. Q is equal to footing pressure on the reinforced foundation and Q0 is footing pressure on unreinforced foundation, both measured in the same settlement. So, VCR was found to range from 1.5 to 4.0 depending on the settlement criteria and the density of reinforcement. Now, come to the stress distribution below the strip footing. We can see here in this graph, at the load increases the soil moves down as it will go like this way. So, at level A, the shape of stress, here is the C and C, C dash and C, this is level B, level 1, this is the reinforcement provided, this is the reinforcement provided at this level and another is at this level. So, this is A 1 B 1 and A B, this is the face of the shear, this is the distance from the center, that is x n. So, here as load increases, the soil moves down and away laterally. This makes like this way. Okay. Assume failure mechanism. Soil zone 1 moves down while zone 2 is moves laterally and upward. The line AC and A dash C dash define the locus of maximum stress. So, we can see here this is A C dash, A dash C dash and A C, this is the zone 2, zone 1 and zone 2. So, here this will go outside of in upward direction like this way, and this is a direct punching underneath of the footing. The bearing capacity ratio VCR, the two terms were used to evaluate the benefit of using RSF. RSF is the reinforced soil foundation. The bearing capacity ratio, bearing capacity to VCR, which is defined as the ratio of bearing capacity of RSF reinforced soil foundation to that of unreinforced and to the settlement reduction factor SRF, which is defined as the ratio of settlement of RSF to that of the unreinforced. Two different type of load settlement behavior were observed in the model footing test. For the first time, the load settlement curve as shown in the figure 3.1, a failure point is not well defined. So, the typical geosynthetic RSF. So, we can see here the benefit of using RSF were then evaluated in terms of VCR at the specific settlement BCRS and RSF at a specific surface pressure. So, which has a well defined point. For this type of load settlement behavior, VCR at a specific settlement, BCR, the ultimate bearing capacity BCRU and SRF at the specific surface pressure were used to evaluate the improved performance of RSF. The figure depicts a typical geosynthetic RSF with the meaning of geometric parameter used in the present study. The optimal value for the reinforcement layout and the effect of type of reinforcement and the soil are determined based on BCR SRF. Now, come to the definition of BCR and SFR. You can see very easily the load is applied here. This is the Q, the value of Q, and this is the QR. We can see here this is the unreinforced soil and this is the reinforced soil. So, we can see for the same settlement the load carrying capacity is now increased from here to here. Likewise, here also this is the unreinforced soil, the settlement for the same settlement we can put it, this is the footing settlement. So, we can see here when it is reinforced soil, the load carrying capacity is now enhanced to QUR. This is the revised reinforced. So, we can see that VCR is QR by Q. So, SRF is equal to SR divided by S. So, we can see here this is the definition of VCR and SRF. Now, come to geosynthetic reinforced soil foundation that is given in the figure. We can see here this is the layer. There are different layers of reinforced bar. This is the width of the footing, this is the width of the footing, depth of the foundation, this is the depth of the foundation, U top layer spacing, this is the U top layer spacing, D is the total depth of reinforcement, this is the total depth of the reinforcement, and the number of reinforcement layer we can easily identify, this is the number of reinforcement layer. L is the length of reinforcement, S is the vertical spacing between the layers, this is the vertical spacing between the layers. So, in this way we can analyze, this is the n is equal to number 3, n is equal to 4, n is 5, n is 2, n is 1. So, this is the soil, this is the footing. So, we can put the reinforcement bar at a different layer to just improve the bearing capacity as we have seen earlier. So, thank you very much. Thank you.